The engine note changes first. Not the steady, reliable rumble that marine diesel engines are supposed to produce, but something higher, angrier, more urgent. The mechanical scream of machinery pushed beyond every specification its designers ever imagined. Then you feel the acceleration, impossible physics that pins your body against whatever solid surface you can find, as the Norwegian patrol boat MTB-47 tears across the North Sea like a projectile fired from some enormous cannon, leaving a wake that looks more like the signature of a destroyer than a coastal patrol vessel that was never designed to outrun anything faster than a fishing trawler. Chief Petty Officer Olav Nordahl crouches in the engine compartment, his hands dancing across controls that shouldn't exist, making adjustments to systems that violate every principle of conservative marine engineering he learned during 23 years of keeping boats afloat in waters that specialize in killing the unprepared. The diesel engines beneath his fingers are screaming at 4,200 RPM when their maximum safe operating speed is supposed to be 2,800. The cylinder head temperatures are climbing into ranges that should trigger automatic shutdown systems. The fuel injection pressures are spiking to levels that threaten to destroy engine components that cost more than most Norwegians earn in a year. But the boat is moving faster than any patrol vessel in the Norwegian Navy has ever moved, faster than the German designers who built the U-boat currently pursuing them calculated was possible for this class of vessel, fast enough to stay ahead of torpedoes that are supposed to be impossible to outrun once they've been properly aimed by submarine crews who understand the mathematics of interception and the physics of explosive warheads designed to crack the hulls of ships much larger than MTB-47. Olav allows himself one glance through the engine compartment porthole, where he can see the phosphorescent wake of the German submarine that appeared out of the morning fog like a steel shark, surfaced and running on diesel power in direct pursuit of the Norwegian patrol boat that was supposed to be conducting routine coastal reconnaissance, and instead discovered a U-boat wolfpack preparing to attack a British convoy carrying American Lend-Lease supplies to Murmansk. The submarine is gaining, but slowly, more slowly than German tactical manuals predict should be possible when a purpose-built military submarine chases a converted fishing vessel that was never intended for high-speed operations in hostile waters. The modifications that allow this impossible chase began 6 months ago, when Olav decided that Norwegian lives were worth more than German engineering specifications, that survival in Arctic waters required machinery that operated beyond the conservative limits that peacetime designers imposed on equipment that might need to function in circumstances where failure meant death rather than inconvenience. What he's done to these engines violates every principle of marine engineering safety, every regulation designed to prevent catastrophic mechanical failure, every guideline intended to ensure that critical machinery operates reliably rather than optimally. This is March 1943. The Battle of the Atlantic has been raging for over 3 years, transforming the ocean that once connected nations through commerce into a battlefield where German U-boats systematically destroy the merchant shipping that keeps Britain fed and armed, where Allied convoys run gauntlets of submarine warfare that claim tonnages of shipping faster than American and British shipyards can replace them. The Norwegian coast provides ideal hunting grounds for German submarines, sheltered fjords where U-boats can hide between attacks, coastal waters shallow enough to complicate detection by Allied anti-submarine forces, geographic positions that allow German naval commanders to interdict supply routes from multiple directions simultaneously. The Norwegian resistance operates a network of coastal watchers and small boat patrols designed to provide early warning of German naval movements, intelligence gathering that helps Allied convoy commanders route their ships around known U-boat concentrations, tactical information that might mean the difference between successful delivery of critical supplies and the kind of convoy disasters that the German propaganda machine uses to demonstrate the futility of Allied resistance to Nazi. Maritime dominance. But resistance operations require boats fast enough to escape when discovered, reliable enough to operate in weather conditions that ground larger vessels, versatile enough to conduct reconnaissance, rescue, and occasional combat missions using equipment that was never designed for military applications. MTB-47 began life as a fishing vessel, built in Bergen shipyards to specifications that prioritized fuel efficiency over speed, cargo capacity over maneuverability, the kind of conservative engineering that allows working boats to operate profitably in commercial fisheries, where every component must justify its cost through years of reliable service in conditions that test equipment rather than destroy it. The conversion to military patrol vessel involved adding radio equipment, mounting machine guns, installing navigation gear suitable for operations conducted in radio silence and hostile waters. But the fundamental limitation remained the engines, reliable marine diesels designed to move fishing boats at economical speeds rather than pursue or escape military vessels built for combat operations. Olav understood that limitation from his first day aboard MTB-47, when trial runs demonstrated that the boat's maximum speed was adequate for patrol operations, but insufficient for the kind of high-speed reconnaissance and escape maneuvers that survival in German-controlled waters would require. Military engagements happen faster than commercial fishing, require acceleration and top-speed performance that conservative marine engineering doesn't provide, demand the kind of mechanical reliability that allows critical systems to operate beyond their design specifications when operational necessity requires performance that peacetime safety considerations prohibit. The engine modifications began with careful analysis of what prevented the marine diesels from operating at higher power outputs, systematic identification of the conservative design elements that prioritized longevity over performance, engineering assessment of which safety margins could be reduced or eliminated if operational lifespan became less important than maximum capability. Marine diesel engines are built to operate for thousands of hours with minimal maintenance, designed to provide steady power output under varying load conditions, engineered to tolerate abuse from operators who understand commercial fishing better than mechanical engineering. But military operations change the mathematics of acceptable risk considerably. Patrol boats that might operate for hundreds of hours rather than thousands can sacrifice long-term reliability for short-term performance. Engines that need to provide maximum power for brief periods rather than steady output for extended duration can be modified to operate beyond conservative design limits. Safety margins that exist to prevent catastrophic failure under commercial conditions become unnecessary limitations when the alternative to mechanical risk is tactical defeat and probable death. The first modifications involved fuel injection timing, advancing the injection sequence to provide more complete combustion at higher RPM ranges, adjusting the spray patterns to optimize fuel distribution within cylinder chambers that were designed for different operating parameters. Olav fabricated custom injection nozzles using machine shop equipment that was never intended for precision fuel system work, creating components that allowed the engines to process fuel more efficiently at power settings that original specifications considered dangerous. The cooling system required more extensive modification. Marine diesels depend on seawater cooling to maintain safe operating temperatures, but higher power outputs generate heat loads that exceed the capacity of standard cooling systems to dissipate safely. Olav redesigned the coolant circulation patterns, installed additional heat exchangers fabricated from materials scavenged from other vessels, created cooling circuits that could handle the thermal stress of engines operating at power levels that would destroy unmodified systems within hours of continuous operation. The most critical modifications involved the turbocharging systems that force additional air into the engine cylinders, allowing more fuel to be burned efficiently. providing power increases that conventional naturally aspirated engines cannot achieve. But turbochargers create their own engineering challenges, requiring precise coordination between air pressure, fuel delivery, and exhaust gas management that becomes increasingly complex as power outputs exceed design specifications. Olav rebuilt the turbocharger assemblies using bearing systems designed for different applications, modified the wastegate controls to allow higher boost pressures, created air intake systems that could provide the volume of compressed air that maximum power operation required. Each modification created new problems that required additional solutions, engineering challenges that multiplied as the engines moved further from their original design parameters. Higher combustion pressures demanded stronger connecting rods and crankshaft bearings. Increased RPM ranges required valve timing adjustments and cam profile modifications. Greater thermal stress necessitated improved lubrication systems and more sophisticated engine monitoring equipment that could provide early warning of impending failures before they became catastrophic. The testing process consumed weeks of careful experimentation, gradual power increases that revealed the practical limits of each modification, systematic evaluation of engine performance under conditions that simulated combat operations without destroying expensive machinery through premature failure. Olav operated the modified engines at progressively higher power settings, monitoring temperatures and pressures and vibration patterns that indicated whether the modifications were approaching their functional limits or could be pushed further without risking catastrophic breakdown. The breakthrough came when Olav realized that the conservative engineering that limited engine performance existed primarily to ensure commercial profitability rather than maximum capability, that the safety margins built into marine diesel design served economic rather than technical requirements. Fishing boats needed engines that operated reliably for years with minimal maintenance, but patrol boats could sacrifice longevity for performance if operational requirements demanded maximum speed for brief periods, rather than economical operation for extended duration. The final configuration allowed the engines to produce nearly 60% more power than their original specifications, transforming MTB-47 from a slow patrol vessel into something approaching the performance of purpose-built military craft. But the modifications came with costs that peacetime operations would consider unacceptable. Engine life expectancy dropped from thousands of hours to hundreds. Fuel consumption increased dramatically. Maintenance requirements multiplied. The engines became temperamental, requiring constant attention from mechanics who understood their modified characteristics. Careful operation by crews who recognized that maximum performance demanded precise coordination between throttle control, cooling system management, and fuel delivery optimization. But when the German U-boat emerged from morning fog and began pursuit of MTB-47, those costs became irrelevant compared to the immediate requirement for speed that could keep Norwegian lives ahead of German torpedoes. Olav engaged the modified engines at their maximum sustainable power setting, pushing cylinder pressures and turbocharger boost levels into ranges that would have terrified the original designers, operating machinery at performance levels that violated every conservative principle of marine engineering but provided exactly the kind of impossible speed that survival required. The chase develops its own rhythm, its own mathematics of pursuit and evasion that transforms abstract engineering into immediate questions of physics and probability. The U-boat commander understands the theoretical performance characteristics of Norwegian patrol boats, calculates interception courses based on intelligence estimates of MTB-47's maximum speed, coordinates torpedo firing solutions that assume conventional marine engineering limitations that no longer apply to this particular vessel. But Olav's modifications have changed the tactical mathematics considerably. MTB-47 is moving faster than German intelligence predicted was possible, maintaining speeds that force the U-boat to operate at power settings that increase its visibility to Allied detection equipment, complicating torpedo targeting calculations that were based on predictable velocity differentials between hunter and hunted. The impossible speed that modified engines provide transforms certain capture into uncertain pursuit, tactical superiority into tactical parity, German engineering advantage into Norwegian innovation advantage. The engines respond to Olav's adjustments like racing machinery rather than marine equipment, RPM climbing smoothly past every red line marked on gauges that were designed for conservative operation, power output increasing as fuel injection timing and turbocharger boost, pressure optimize for maximum performance regardless of long-term mechanical consequences. The boat's hull begins to exhibit planning characteristics that its designers never intended, rising partially out of the water as hydrodynamic forces lift the vessel into semi-flight across wave surfaces that would normally impose speed limitations on displacement hulls. Through the engine compartment, Olav can feel the hull stresses that extreme speed imposes on structures never designed for such loads, can hear the mechanical notes that indicate approaching limits for systems operating beyond their engineering specifications, can monitor the temperatures and pressures that show exactly how close the modified engines are to catastrophic failure. But he can also feel the increasing distance between MTB-47 and its pursuer, the growing margin of safety that impossible speed provides against torpedoes that cannot adjust their targeting calculations fast enough to compensate for prey that moves faster than predator assumptions allow. The German torpedo launch comes at maximum effective range, white wakes visible against dark water as two projectiles streak toward positions where MTB-47 should be if it were operating at conventional patrol boat speeds. But Olav's engine modifications have provided exactly enough additional velocity to place the Norwegian vessel outside the torpedo engagement envelope, moving fast enough to stay ahead of weapons designed to intercept targets with predictable performance characteristics, maintaining speeds that transform German tactical advantage into Norwegian survival margin. The U-boat commander faces the choice between continuing pursuit that reveals his position to Allied forces or breaking off engagement with target that has demonstrated impossible performance characteristics. The mathematics of submarine warfare favor stealth over speed, concealment over pursuit, tactical patience over immediate engagement when targets prove more capable than intelligence estimates predicted. The German submarine begins its emergency dive, disappearing beneath North Sea surface that will hide its retreat, but also eliminate its ability to continue pursuit of Norwegian patrol boat that has proven faster than German engineering assessments considered possible. MTB-47 maintains maximum speed until the U-boat disappears completely, until sonar contact indicates that the German submarine has committed to underwater operations rather than surface pursuit, until tactical safety margins suggest that immediate danger has passed and engine preservation becomes more important than maximum performance. Olav begins the careful process of reducing power settings, allowing cylinder temperatures to decrease gradually, monitoring engine parameters as the modified diesels transition from emergency performance to sustainable operation. The return journey provides opportunity for complete assessment of what the chase has cost in terms of engine wear and mechanical stress. The modified systems have operated beyond their design limits for over 2 hours, generating power outputs that peacetime considerations would consider catastrophic abuse, maintaining performance levels that have probably reduced engine life expectancy by hundreds of operational hours. But they have also provided exactly the kind of impossible speed that allowed 4 Norwegian lives to survive an encounter that should have ended with torpedo explosions and rapid descent to North Sea bottom. The technical report that documents the chase becomes classified material that influences Norwegian resistance naval operations for the remainder of the war. Olav's engine modifications prove applicable to other patrol vessels, providing performance improvements that transform coastal reconnaissance from suicide missions into operations with reasonable survival probabilities. The techniques he developed under operational pressure become standard procedures for small boat operations in hostile waters, engineering solutions that prioritize tactical performance over conservative reliability when survival depends on speed rather than longevity. British naval intelligence requests detailed information about the modifications that allowed a converted fishing vessel to outrun a purpose-built military submarine, seeking technical innovations that might be applicable to Royal Navy coastal operations in waters where German naval superiority makes conventional tactics inadequate. American engineers study Olav's work as part of PT boat development programs that require maximum performance from small vessel platforms operating in Pacific theater conditions, where speed often determines survival probability in engagements with Japanese naval forces. But the broader significance extends beyond specific technical applications to questions about the relationship between conservative engineering and operational necessity, between safety margins and survival requirements, between following regulations and achieving results when regulations prove inadequate to circumstances that their authors never anticipated. Olav's willingness to operate machinery beyond manufacturer specifications demonstrates that technical limitations are often more psychological than physical. That expert opinion about what is and isn't possible can become obstacle to innovation when innovation becomes requirement for survival. The Norwegian resistance continues coastal operations using patrol boats equipped with modified engines that provide tactical advantages measured in knots and survival percentages. Small improvements that accumulate into strategic benefits when multiplied across hundreds of reconnaissance missions and supply runs conducted in waters where German naval forces maintain superior numbers and firepower. The engine modifications that seemed like desperate expedients proved to be accidentally superior design, achieving better results through different methods than conservative marine engineering provides. Years after the war ends, Olav establishes a marine engine modification business that serves commercial fishing fleets and pleasure boat operators who need performance that standard marine diesels cannot provide. Customers who understand that some applications require machinery that operates beyond conservative specifications if operational requirements demand capabilities that peacetime engineering doesn't anticipate. His wartime experience with engine modification influences the development of high-performance marine propulsion systems that balance reliability against capability, that provide maximum power when needed, while maintaining reasonable service life under normal operating conditions. The principles that Olav discovered under combat pressure, that conservative engineering often masks unexploited capability, that machinery can be modified to exceed specifications when operational necessity justifies mechanical risk. That innovation emerges from willingness to question expert opinion about limitations. These lessons prove applicable far beyond marine engineering. They influence design philosophy in industries that require maximum performance under unpredictable conditions, where standard solutions prove inadequate, and survival depends on finding approaches that exist outside normal procedures and conventional wisdom. Modern high-performance boats incorporate design elements that trace directly to modifications that Olav developed under survival pressure, engineering solutions that were originally field expedients but proved superior to conventional approaches when tested under operational conditions that revealed the practical limitations of conservative design philosophy. The engines that seemed impossibly fast in 1943 now represent standard performance for recreational powerboats, marine propulsion systems that routinely operate at power levels that would have seemed fantasy to engineers designing equipment for commercial fishing operations. The North Sea continues to challenge every vessel that operates in its waters, weather conditions and tactical situations that test both machinery and human judgment under circumstances where mistakes become catastrophic quickly. and survival depends on maintaining performance when conditions exceed normal operational parameters. But sometimes, when modern patrol boats conduct training exercises in the same waters where MTB 47 outran a German U-boat, instructors tell the story of the Norwegian mechanic who proved that impossible was just another word for untested, who demonstrated that survival sometimes requires the courage to operate machinery beyond manufacturer specifications when manufacturer specifications prove inadequate to operational reality. The engine note that saved 4 Norwegian lives still echoes in the design of marine propulsion systems that push the boundaries between reliability and performance, between conservative engineering and operational necessity, between following regulations and achieving results when regulations fail to address circumstances that demand innovation rather than compliance. Olav saw possibility where specifications saw limitations, recognized opportunity where training saw only risk, understood that survival sometimes requires techniques that peacetime safety considerations prohibit, but wartime necessity demands. The wake that MTB 47 left across the North Sea that March morning continues to ripple through marine engineering philosophy, through the understanding that machinery can be modified to exceed specifications when operational necessity justifies mechanical risk, through the recognition that innovation often begins with the willingness to question expert opinion about what is and isn't possible when survival depends on finding solutions that exist outside conventional approaches and conservative design limits. If stories like this remind you that impossible is often just another word for untested, that innovation emerges when normal solutions prove inadequate to extraordinary circumstances, then perhaps there are other moments when refusing to accept engineering limitations created breakthroughs that changed how we understand what human ingenuity can accomplish when survival depends on pushing machinery beyond every specification its designers ever imagined possible.